But today I want to finish up Bainite and move into twins and martensite. Friday, and just as a quick overview, since it was before the break, the fall break that we last met, just remind us that Bainite is a lath-like structure where we get these sheaves made up of little subunits of ferrite growing into the austenite matrix, and then after we get carbon that diffuses out, and the exact mechanism of the Bainite nucleation and growth is fairly controversial. Some people believe it is a diffusional transformation. Others believe it is diffusionless. And that comes about because it has aspects of both, right? And it happens at a temperature below Widmanstätten ferrite, but above martensite, and it is a displacive transformation. So there is a shear associated with it, not just diffusional growth, right? And the key aspects is that we have a it's not athermal. It takes time for it to occur, right? And that time is a strong function of temperature. And it doesn't necessarily go to completion, right? We have a Bainite start temperature at which the reaction begins. And depending on the temperature that we hold at, we may not go completely to finish. And that if this occurs, that we have to have nucleation and growth both need to stop at some point. And the reasons for that is basically where we left off on last Wednesday. Okay. So we have two basic forms, upper Bainite and lower Bainite. Upper Bainite, we transform, and then all the carbon diffuses out, and we get layers of carbides in between these. In between the subunits as the sheath grows, right? And we have a shear associated with it, which gives us relief on the surface. But what happens is we have plasticity that forms. This is fairly large elastic strains that happen, very large strains that happen, and it's too large to be accommodated purely by elastic means. And whereas with, remember, in Widmanstätten ferrites, you would have two variants with opposing shears grow next to each other to relieve that strain. With Bainite, we get plasticity. So you have the Bainite subunit that forms, and then you get plastic slip next to it. And we can see this in atomic force microscopy measurements of the surface. Right. So here, this is our Bainite, our ferrite region here. And you can see we have a raising of the surface, and then we have plastic deformation that brings it back down. Right. And that the carbides form after the ferrite. So it's a two-step process, and the formation of the carbides is not actually essential to the Bainite reaction. Right? So we grow the subunits, then the carbon diffuses out and forms the carbides. And if we have alloying elements such as aluminum or silicon, which retard the formation of the carbides, then we have a bainite microstructure that is, the carbon still diffuses out, but we have ferrite subunits separated by austenite, which is supersaturated in, or enriched in carbon. Right? So the carbides themselves, the cementite is not integral to the formation of bainite like it is in pearlite. Okay. Lower bainite is similar, except the carbon doesn't completely diffuse out, and we get carbide layers within the bainite sublasts. For most of the time, we get a single variant. Remember, there's an orientation relationship that forms. So we get a single orientation of the cementite within the lower bainite lath. But typical of steels, sometimes we get multiple variants. So usually you'll see a bunch of parallel cementite plates. Other times you'll see plates that are at sort of nearly orthogonal angles to each other. And some really nice work from the UK in the late 70s, early 80s did a lot of work to show that really upper and lower bainite are distinct structural units. It's not just the fact that carbon diffuses slower, and that there are actual different TTT curves that intersect for lower and upper bainite. And depending on your cooling schedule from the same alloy in the same sort of range, you can get a heat treatment that gives you all upper bainite or all lower bainite, depending on where your cooling rate takes you across the nose of that curve. Yeah.
Just out of curiosity, there's like 3 different separation points there.
So these lines, right? So this is a TTT. So if we hold it at constant temperature, the solid line typically denotes 50% transformation.
Oh,
right.
Line.
Right, and then this is 10%, 90%, or 5%, or 95%, exactly. Whatever it is for this one. This graph, unfortunately, doesn't have a legend, but that's typically the right. Don't you remember my exciting TTT diagram exercise from 3321? Okay, so basically back to where we left off on Wednesday, and this is something that confused me the first time I saw this. So I do want to take time and go through it and make sure everyone understands it. So basically, there's a lot of disagreement as to whether bainite, what role diffusion plays in bainite formation, right? Especially upper bainite, we know that carbon partitions to the austenite. Okay. Now, in martensite, as we'll see, we can easily tell it's diffusionless by measuring the carbon content before and after, because we're quenching it. It happens so fast, right, that we know what the carbon concentration is in our austenite from our phase diagram. We quench down. We immediately go to austenite, but we cool fast enough that the carbon doesn't have time to diffuse any significant distance, right? We can quench really fast. We can form martensite really fast. Then we can measure the carbon content in the martensite after the fact, and we see it was the same as what the austenite was before we quenched. And so therefore we know that martensite has to be diffusionless. Bainite forms at a bit of a higher temperature, enough that the diffusivity of carbon is still very, very quick, right? And the plates are very small, so the diffusion lengths are not that long. right? We're sort of thinking on a micron length scale, and carbon's interstitial, and we're at a high enough temperature, it takes less than a second for carbon to hop out of the bainite sublath. And we know that the bainite reaction takes time, right? It's not instantaneous like martensite. So what we can't do is we can't measure the original composition and post-formation composition in situ, right? So we don't really understand the precise role of carbon. And based on experiments, there's three sort of hypotheses that are consistent with what we know. We can either say the carbon partitions during growth so that the ferrite never contains any excess carbon, right? Or we can, that's one extreme. The other extreme is that it can be diffusionless and the carbon is trapped by the advancing interface and it doesn't diffuse. Carbon doesn't diffuse out at all until after the bainite reaction is complete. Or there's an intermediate case where some carbon can diffuse and some is trapped, right? And so instead of a completely supersaturated ferrite, we have a partially supersaturated ferrite. And we can't really tell by looking or by experimental methods which of these is true. So we have a couple different models. This is why there's so much argument about this. People who say that it's diffusion controlled basically say that it's just a non-lamellar eutectoid reaction and its growth is very similar to Widmanstätten proeutectoid ferrite, right? And it basically assumes that the carbon has all diffused out into the austenite, and then the carbides, right? If we have ferrite that's growing, we have carbon that's partitioning, right? Eventually that carbon level, just like in perlite, gets to a high enough level that we nucleate carbides, very similar to the quiz question today with the nucleation of cementite and ferrite, or cementite and perlite, right? And so if that's the case, the carbides are nucleating and growing in the austenite, so that means the carbide should precipitate on the austenite side of the ferrite austenite boundary, right? And for a lot of upper bainite, we see that that is the case. But for lower bainite, a lot of it, experimental evidence shows just the opposite, that the carbides are nucleating in the ferrite side, right? Which is odd because that's where we're lowering carbon, right? Of course, in lower bainite, you can make the argument that we're diffusing slower and the ferrite is more supersaturated than the austenite is carbon enriched, right? There's these sorts of things at play, but it's very difficult to explain why you would get the carbide precipitates that are growing. These are the intersheet carbides, right, that are in between the bainite subunits. Why that would start in the ferrite rather than in the austenite. On the other hand, we have the diffusionless transformation model. And for this, we have to look at our phase diagram and our free energy curves, right? And so for the transformation to occur, was it an interesting question at least? Oh yeah. So to be diffusion, we always have to think about what's going on with our free energy, right? And so basically, if this is going to I wish I had a pointer. Oh, I do. I'm an idiot. Okay. Right. So if we're at a point, here's where our austenite and our ferrite and austenite free energy curves are here, and if this is where they intersect, so at this point, our free energies are even, right? And so if we partition, right? So say we're here at this carbon concentration. There's my pointer. If we're here at this carbon concentration, somewhere to the left of T naught, by transforming to austenite, we locally lower our free energy. Transforming to ferrite, I'm sorry. We locally lower our free energy. If we're to the right of this curve, by transforming to ferrite, we locally raise our free energy, right? So what that means is that this T naught point is the greatest carbon concentration that we can form Bainite by a diffusionless transformation. Because remember, we're not changing our carbon concentration in a diffusionless mechanism. And this picture, well, so seemingly obvious to me now, when I was a student, this confused the ever-living heck out of me, right? And it was this, because I kept looking at the common tangents and thinking that, well, if it's equilibrium, the common tangent has to be horizontal. But that's not true, right? It's all about what's happening locally as I go from austenite to ferrite, right? Whether I'm dropping here or whether I'm raising, right? And so this T naught line, where these two curves intersect, moves at lower temperatures, is going to go to higher carbon concentrations, right? So we get this T naught line that straddles our equilibrium, right? Composition in alpha, composition in gamma, right? We get this T naught line that straddles and it moves farther to the right, and that's the mechanism behind the Bainite start and Bainite finish temperature, right? As if that were at some temperature, intermediate temperature, we hit T naught carbon concentration in our austenite before we can continue, right? And if that's actually true, we should see that our concentration in the austenite should stay basically at that T naught line, and we do see that. So basically, what we can say is that there is a diffusionless aspects to this, right? But we know that there's something. We know carbon is diffusing out, right? And we know it's not instantaneous like martensite is. So there's aspects of both. My personal opinion is that it's not just the shear, but there's a shuffle mechanism that happens, that you need a short-range atomic shuffle that has a diffusional aspect to it, followed by a rapid shear. But there's lots of different people who think there's a ton of competing Bainite nucleation theories, right? So what's important to understand is that it's an unsettled question. There's aspects of the diffusional transformation, there's aspects of the diffusion. Okay. So let's take a look at our kinetics here. So basically, we have a subunit that forms, right? There's an invariant plane strain shear associated with the formation of this subunit, right? And the larger it grows, the more overall strain there is that has to be accommodated, right? That has to be accommodated by plastic deformation. And basically that plastic deformation right? We have dislocations that are passing through. We've got a high dislocation density immediately surrounding the lath, right? So that means that material is significantly work hardening around this little bainite sheath very locally, right? And basically the energy balance goes wonky, and this subunit gets halted, right? Then in a nearby, we have a new subunit that nucleates, right? Forming this sort of sheath structure. And what's important to know is that each subunit grows very fast, but because of the interconnected nature of all the subunits, right, the overall growth rate of the sheath is significantly less than the growth rate of the individual subunits. This picture here is a little confusing because it shows the subunit here. This is the rate, and this is the sheath growth rate. Really, the subunit only gets so long, right? So then this should go to 0, right? It's sort of missing that fast rate then to 0 because it halts. Okay, and then after that we get carbides that form, right? And this transformation occurs more slowly at higher temperatures, so we have less driving force, right? We have less driving force, but plastic deformation is a lot easier. So at higher temperatures, we have the sheaths grow slower, but the individual subunits can grow longer because we have easier plastic slip. So we're dissipating less energy. We're work hardening less. So basically, we have bainite that ends up looking like a typical nucleation and growth process, right? We have a nucleation time. We have an increasing transformation rate, and then a slowing of our process, right? And we have, as we lower the temperature, we go from a regime where we're growing upper bainite to a regime where we're growing lower bainite. And we can really, again, there's a lot that we don't understand yet, but we can basically think about it as going into a regime where we diffuse all the carbon out to a regime where we're now also nucleating a fine distribution of carbides within the bainite structure. Okay, so this leads to something interesting. We always talk about how strength and toughness are opposite properties. But we end up here, lower bainite is actually tougher, right? Because we have less, it's stronger because we've got all these obstacles here, the plastic deformation in the ferrite. But we also have less of this interconnecting brittle frays, right? So we actually have something that's lower bainite is tougher and stronger than upper bainite.
So in terms of toughness, you're starting out with upper bainite, and that's going to be less tough than lower bainite, but then it goes into martensite, and that's less tough than lower bainite. It's kind of like a carrot.
Yeah. So martensite is exceptionally brittle, right? Because you've got a BCT structure, right? You have very limited dislocation. Even BCC martensite is.
There's BCC martensite.
Yeah. Depending on the carbon content, you can actually go to BCC martensite. Okay, so that sort of wraps up the physics of bainite. I do want to hit this acicular ferrite, right? Which is basically these are ferrite plates that instead of forming nice layers, form this mess of disorganized plates. So here we have bainite forming nice regular. The subunits are fairly parallel. Acicular ferrite, they're just pointing any which way. I like the term acicular bainite because it's more descriptive of what it actually is rather than acicular ferrite, because it mimics bainite quite a lot. They form very similarly, except bainite forms in sheaves, right? And they nucleate from the austenite grain boundary and move out. Whereas acicular ferrite nucleates in the interior of the austenite grain, right? And so it nucleates with, it grows into this disorganized structure of plates because there is nothing forcing it to be nice and regular. Remember, bainite forms the Kurgyamov-Sachs-like orientation relationship, right? And we see the same thing, right? We see growth, right? We're limited by the T0 carbon concentration, right? And so we're nucleating heterogeneously sort of at inclusions. And so if we have a sample that forms acicular bainite, if we, an alloy, if we like remelt this to remove the inclusion and we go through the exact same cooling schedule, we'll get bainite rather than acicular ferrite. So it's really just bainite that's nucleating interior to the grain rather than at the grain boundary, right? And if we increase the grain boundary surface area, we can do the same thing, right? So if we have big prior austenite grains, we get acicular ferrite. If we have small grains, right, a lot more surface area, right? Remember, surface area goes by what with respect to the radius? Right, squares, right? And so, right, we're making the grains a little bit smaller gives you a drastic increase in surface area, a lot more nucleation sites. So if we make our austenite grains smaller, we eliminate acicular ferrite. Right? This is very much like, think about it in the same way as you do about idiomorphic versus allotropomorphic ferrite, that diffusional ferrite, right? If you have lots of nucleation sites, you're going to grow ferrite at the grain boundaries, right? If you have inclusions and intermetallics in the grain, you're going to grow idiomorphic, right? Okay, so that we can also go the opposite way, right? If we make our grain boundaries ineffective as nucleation sites, right? Which means if we grow some allotropomorphic ferrite on it, right, a little bit of boron will do that, right? Drastically reduces the grain boundary energy, which means we have less favorable nucleation sites for bainite. We'll go grow acicular ferrite rather than upper bainite, right? Okay, and so much like martensite, right? Bainite is. When I said lower bainite's tougher than upper bainite, the stuff's still not tough, right? You still have layers of brittle carbides separating, right? You've got plenty of places for cracks to nucleate. And the ferrite itself, right, the bainite itself contains fairly small amounts of carbon. So the tempering is not as dramatic as it is when we look at tempering of martensite. But basically, if we have retained austenite, if our bainite reaction doesn't go all the way to completion, we still have retained carbon and this retained austenite, and this austenite is carbon enriched. So if we temper it at temperatures where we have mobility of our carbon, this will decompose this enriched austenite into ferrite and other carbides, right? Basically, we'll be like growing perlite within our bainite, right? And this is, if we have strong alloying elements that are strong carbide formers, such as chromium, vanadium, molybdenum, and niobium, right? By tempering, we form more stable carbides than cementite, right? We form these intermetallic carbides, right? And these are much more stable, and so we get a additional hardening, secondary hardening that comes from tempering the bainite. And this is what sort of the tempered bainite structure looks like, and optically, I mean, it looks like tempered martensite. You have to be really good to be able to pick out differences between these steel structures after they've been through a couple heat treatments. All right. Okay, so last couple slides, and we'll wrap up a couple minutes early. Okay, so role of the different alloying elements. Carbon, as you might expect, the amount of carbon in your system is going to have a huge effect on the range of temps over which bainite forms, right? And you can think about that in terms of the shape of that T0 curve, right? So lower, right? And then in terms of other elements, are all going to basically have the effect of lowering the Bainite start temperature, right? So carbon, this is just a rough empirical fit that tells you what the Bainite start temperature is going to be as a function of your alloy composition, right? We can see carbon has the greatest effect, right? And then manganese, molybdenum, chromium, and nickel, right? All those alloying elements depress our Bainite start temperature.
So you just put like the weight percent number in for the names of the elements.
Yeah. Yep. Right. I don't think you'll ever actually have to use this. It's just sort of I like it just because it's easy to, since someone went through the trouble of fitting it, it just shows you sort of what the relative effects are. That carbon has roughly 3 times the effect of the next greatest element at reducing the Bainite start, right? And the amount of carbide that you're going to form, you're going to have to balance by the amount of carbon, right? So the amount of carbide depends on the concentration of carbide. So we can't raise this up too much, right? Because we don't want to destroy our other properties, mostly toughness, right? So we have an optimal carbon concentration of about 0.4%. Okay. So in plain carbon steels, right, our Bainite reaction sort of hides behind rapid ferrite formation, right? So we have to add substitutional solutes to retard the ferrite and cementite reactions. Right? We talked about that before, the perlite growth, right? So basically, that has the effect of pushing the nose of these curves in the TTT diagram over here to the right. So that means with a cooling curve, you can miss the nose of the ferrite curve and enter into Bainite, right? So if you just have plain carbon steel, if you cool, you're either going to have 2 things happen. You're either going to go through the nose, and then you're going to get a pearlitic steel, or you're going to go in front of it and hit martensite. In a plain carbon steel, it's very difficult to hit Bainite, right? But if we, by some smart alloying, we can push this to the right, come down into the Bainitic region, right? Still difficult because we need to avoid this martensite start, right? But we can push Bainite to the left with molybdenum and boron, right? Remember, boron is going to retard the ferrite reaction, oddly enough, by giving us a grain boundary layer of ferrite that makes it difficult to nucleate perlite. Right. But so if we play with these concentrations, and we're talking, very small amounts of boron, 0.002%, right? So this is, right, percent is 100, is hundredths, thousandths, 10 thousandths, 100 thousandths, so 20 part per million. Boron and less than 1 weight percent molybdenum, we can get fully Bainitic steels. Okay. So what the role that Bainitic steels play is we want cheap steels, right? So we need moderate strength needs with a low amount of alloying elements, right? So we want things that are cheap, but still stronger than perlitic steels, right? And that's basically the range we're playing in, right? And if we look at alloy compositions, carbon, silicon, manganese, molybdenum, boron, right? These become fully Bainitic, very little martensite, using simple things like normalizing heat treatments, right? If we want to go through, this is basically just sort of like a flow chart of how we can, the range of Bainitic steels that you can get, right? And sort of compositions, right? So our as we go up for each of those different classes, what the alloy compositions look like, right? And so you can think about the main categories of these. We can think about ultra high strength alloys, which are a mix of bainite, martensite, and retained ultra high strength alloys, right? And we get high hardening by this magical pixie dust composition here, basically allowing us to prevent cementite formation. Medium strength alloys, which we use in most of our forgings, in camshafts and crankshafts, and crash reinforcement bars, the pillars, in door frames and things like that for automotive use, fall into this medium strength alloy regime. Creep resistant bainite, creep resistant alloys. The main thing is we want to throw some chromium and molybdenum in there to enhance hardenability and to precipitate carbides, right? Basically, the more carbides that we have in there, the more that we're impeding defect motion at higher temperatures, the more creep resistant our alloy is going to be. And then there's this other weird class, which are inoculated alloys. Which we throw some non-metallics in there to give us heterogeneous nucleation of acicular ferrite, right? And those are used in places such as oil rigs, right, where we begin to we want enhanced properties of the fact that we have plates going in all different directions rather than layered plates, right? But for the most part, Bainitic steels are sort of fill this niche of moderate strength but very cheap to produce, right? There's a couple specialties, but that's really the range that we want to think of with Bainite. Okay, so on Tuesday we start twinning and martensite, and then on to the whole heat treatment schedule of steels and more about specific alloys.